For my part, I will just start with this presentation of the CO2 network simulation. And what we did in this project was to start with a model of a CO2 network and also implement a control strategy, how we can heat and cool at the same time, and make some suggestions for the safety measures, so how we can keep the CO2 network safely in operation. First of all, CO2 is not the same as water. We just use the evaporation heat of the CO2 to heat our user stations and also the condensation of the CO2 to keep the cooling possible. And the whole network approach was to have at the same time cooling and heating demand from different users, and also just supplying them by one primary network. And as equal to water during heating and cooling, the mass flow is defined by the energy demand. And here we are only defined by the heat of evaporation of CO2 or the heat of condensation of CO2 in the user stations. And interesting on this topic is the vapor pressure of CO2. As Robert already mentioned, we have a vapor pressure of 50 bar in our model network, and this has a resulting temperature of about 14 degrees Celsius at the boiling point. And this is why we are operating at this temperature. So we suggested to keep about 10 degrees Celsius at the liquid line and at least 15 degrees Celsius at the vapor line to ensure enough spread to the boiling point. And simulation is a topic where we have just the model parameters. I try to explain you this type of simulation where you solve several equations at the same time at every position of the network. And if you have a network like this, where we have our central heating station and also 5 consumers around, and we have here a separation from vapor to liquid line. So we have the outer line is the vapor line where we can have the hot CO2 with the 15 degrees Celsius, and in the inner circulation there's this liquid line. And with this model we have been able to not only to solve these equations for the mass flow, but also to gain information about the energies needed for our heat exchangers and also pump pressures, etc. And in this project, it was possible to make an estimation about the costs of the whole equipment needed for such a CO2 network, and depending on the demands of the consumers. The simulation was also possible to make a control of the CO2 loop network. And in the next step, I will show you how this user station was realized. So it's not only the simplified approach of an heat exchanger connected vapor to liquid, but it's also an approach where we can say, okay, with one user station, you can heat and cool at the same time, and you only want to pump liquid CO2. So in the first direction, if the consumer transfer station is in heating mode, so you as consumer want to heat, you want to consume from the vapor line, you're opened and you're condensing CO2 on a heat exchanger, and on the lever of the heat exchanger, a control valve is opened or closed depending on the demand, and giving the condensed CO2 back to the liquid line. And in the other direction, where the heat transfer station is operating in cooling mode, you're opening a valve to the liquid line and pumping liquid CO2 to your heat exchangers, and the PID controller again controls the flow of the CO2, and superheated CO2 is added to the vapor line. What was interesting about this thing was that you don't have only this consumer station, but also the problem of some points where nearly no flow is existing in the network. And therefore, we thought this could be a problematic phase in the operation. So we had the difficulty that it's not only a water network where you have the forward flow and return flow in your network, but also the need to evaporize or condense the CO2 to get to the liquid, vice versa, the vapor line. So it was clear we have to ensure at the whole network that the flow going from one consumer to another, here the green points, is taken into account. And then if this, if the sum of the flow going to the next consumer is too low or next to zero, we have to take into account the cooling of the liquid in the or vapor in the pipe. To ensure this this prevention of the phase change, Robert already mentioned it. It's necessary to keep distance to the boiling point of the CO2, and there are two possibilities. Even combinations are possible. The first one is a differential pressure of vapor and cooling line. For example, if the boiling point of CO2 is laying at 44 bar at 9.1 degrees Celsius, so this is the ground temperature of the CO2 network in Denmark. So if you are having a pressure above this this 44 degree, this 44 bar, you are in a defined liquid state in the liquid line. And if you are below with 43 bar, for example, you're in a defined gaseous state. And this could be a solution. But our attempt was another one because of the fact that there are also some flows in between of the consumers, and you want to ensure that you have always the right temperature at the consumer. Our approach was to superheat and subcool the CO2, so controlling the temperature of the network to ensure enough flow and duty in the network to keep it at the clear phase position. And here you can also see at this layout that you have to keep the vapor phase in state. You just have to add another consumer at the network to get an active control of the duty of your network. So if the last consumer is in need of more energy or less energy to keep the phases in shape, you can control this actively as network provider, and you're not in charge of the consumers. So we added this phase change prevention consumer, as I said, another consumer at the end of the network. From the size, about a third of the size needed for one consumer. And we tried to ensure here the safe state by keeping the temperature above 15 degrees Celsius in the network. And it was possible to increase even the energy efficiency with this system, because the buffer we installed for this phase change prevention could also be used for energy saving by peak shaving, and has here a double usage in this format. And because it's research project, we also wanted to be as energy efficient as possible. So we are just storing the energy in this buffer we need for this temperature switches, and we are just trying to gain the energy by another heat pump. Yeah, we also tried to size this this buffer vessel according to the highest demand in the year. So we have enough energy reserved to keep this buffer in operation. And the buffer had a height of about 36 cubic meter, and could be possible that it's that the peak shaving could be even more with a bigger buffer, as you know. But in our operation, we tried to shave about the upper 10% of our end duties. And this was possible with this nearly 40 cubic meter buffer, operating between 5 degrees Celsius and 55 degrees Celsius in this propane heat pump of the energy store. And to show you the whole network, I prepared also this slide where you can see the integration of the user station I showed you. And we have this for every consumer, including a small pump, making the pressure difference of the network. So there was no central heat pump needed at this network type. And this was here at the last consumer, the consumer 5. Right at the end, we have another heat prevention system we have been speaking about, and this would be here added. We tried to simulate the whole system dynamically to compare it also with the simulation of forward energy. The difference was that they had an open source software, not SNU, and in this one we have the SMISIS software, which is a commercial software. And here we can also simulate every dynamic state. So we have been provided by load profiles of the 5 consumers, and they were integrated into the simulation module, and we ran the simulation over given time periods in over 2 weeks, and also a yearly time period, just to ensure the stable running of the simulation system. Okay, thank you for your attention.